this in waiting hours.
So before we start the course, I just hear some feedback, and let me, so to say, preach about activity in academia. It is my impression, other people might have another one. If some of you may touch academic environment and dislike the uncertainty of outcome, too many unknowns and uncertainties. If you select more like industrial environment, there will be much less uncertainty. You will have well-defined goal, well-defined outcome, and some people may be happy, but there will be much less freedom and much more pressure. So it's like conservation law. Less certainty, but more freedom. So who we are and what are we doing? Well, thanks again for presenting last time, and thank you for keeping up your mood and strength to keep coming to the meetings. We have completed chapter 1. You are certified experts in molecular model building. I hope you enjoy this title and practice building a lot of models. We will need your skills further in the course for building models that we will characterize electronically. But now for about 2 months, we will focus more on the electronic properties. So supposing that geometry has already been provided from I don't know where, but looking for the orbitals, molecular orbitals, or we'll call them different ways. So how electrons find their preferred spots in the space. If you are well familiar and comfortable with the concept of Slater determinant, you may lift up and wait. Or you may stay if you are well aware, but you would enjoy hearing about it more, or come to the board and help. So, what are we going to get at the end of the meeting? Nothing. It is too early to get any practical benefits. We may get just general directions, just formulate problems that we are going to solve for a month, and sketch the way to approach them. So our general goal somewhere here is to get right theories that are implemented in the right zoom. Very good. So right theories and right software, and there, yeah. Next chapter. Okay, I'll just freely speak and then show some. So we already realized main challenge of computational chemistry as well. We know the goals to predict observables, and we know the main challenge that there are too many degrees of freedom. When we wipe off, when we forget about nuclear degrees of freedom, when we start to believe that they are point charges, the problem is easier and quicker, but not substantially. We had like 10 to the 100, and now you may have 10 to the 90 grid points if you want to find solution in numerical form. So we will look at the challenges and form the way to resolve them. So let me summarize what we are going to get by the end, so that if you need to leave earlier or if you lose concentration, you do not suffer. We are going to practice separation of variables. We are going to consider atomic orbitals as building blocks for overall electronic wave functions. And we are going to get the background ideas for so-called Slater orbitals, which are, you may write it down. I'm going to say something that looks important for me. So Slater orbitals are protocols. It's a protocol how to construct overall wave function out of building blocks, out of atomic orbitals. So if you already know it, then you can just, and if you hesitate to leave, you can just lean back and relax. So it's not a mythological character. He is a real person who was living not so long ago, and some of you are going to visit Sunnable conference organized by University of Florida. When I was as a postdoc at the University of Florida, across my office there was a wall with some aquarels. They were on plaques. And so when John Slater was working at this institute, at free time he was making these aquarels. So it's my best connection to John Slater. He was visiting the same conference that some of you are going to visit, so you will also have connection to tell stories later on. So we agreed that there are electronic and nuclear coordinates. There is a molecular Hamiltonian. We split degrees of freedom and equations, overall molecular Schrödinger equation, onto electronic and nuclear part. And then for electronic part, we stopped at this equation, where we have both interaction between electrons and interaction between electrons and nuclei, with understanding that things do depend on positions of ions. And when we were, this is part that we have already completed, when we are going towards nuclear degrees of freedom, we accept point charge approximation. We have this Newtonian equations of motion for this concept of potential energy surface. And you all can make this flow chart for the algorithm of optimization if someone decides to make like a quiz, right? This will not be a surprise for you to fill these boxes. Good. I don't want to waste my and your time, but I just want to read in your eyes that you are ready and you know this. Good. And in the homework that I'm going to collect, you will show how you did practice finding minimum of parabola, not by your strong human intelligence, but by following silly algorithm, right? And you may have found that minimum of y equals x squared parabola is 0.5 or minus 0.3, something like this, based on the algorithm tolerance, right? Well, I'll check your homework. I probably need them to collect earlier before we all get too excited about the class material. So, how many types of terms in molecular Hamiltonian you did observe? Right? 5. 2 kinetics and 3 potential. If we accept that nuclei are point charges, how many terms we will stay with? It's not on the camera. 3, right? So we remove everything that is related to nuclei distance and nuclear kinetic energy, and any good memories about nuclear positions will be stored in the distance from electron to nuclei and in the eigenenergies of electronic states that need to nuclear. Oh, we'll have little memory about nuclear positions. Good. Yeah, eigenenergies will depend on positions of nuclei. So from now on, you are allowed to forget everything we covered before now for 2 months. Then you will need to quickly recall it back. So we will be looking only on this equation for 2 months, and which in narrow sense is the task of computational chemistry. And we will look for several theories. When one is talking about computational chemistry theory or computational chemistry method, it means a set of approximations and algorithms that allows to find this phi sub A and E sub A in one or another way. Since we know that everything is approximate, neither one of these theories and methods is exact. Everything has error. The question is how big the error and how much you pay for it. So if error is less, we need to compute for whatever system administrator allows, like long queue, 1 week, or maybe 1 hour on 10,000 processors, if the cluster has it. So there is a balance between precision and resources. Okay, so here's our favorite example. Remember, we were counting number of degrees of freedom. We were counting the number of nuclear, ionic degrees of freedom in the past. We were overviewing a couple of very simple molecules and counting how many independent degrees of freedom are needed to consider nuclear wave function. Now, we don't care about nucleus, we care about electrons. So if we do want to find electronic wave function, it means function that depends on positions of all electrons. And number of independent degrees of freedom is number of electrons times 3. So if it is a for estimate, we can once again believe that we discretize space, and for each degree of freedom we have about 10 grid points. And then we build function as different values of phi as function of this grid points. First, second, third, right? So for 1 degree of freedom in our experiment for thought, then we never go to do it in practice, but we can assume that 10 grid points is sufficient, right? Then if you have 2 degrees of freedom, it will be 10 by 10, 100 grid points, 2-dimensional function. If it will be 3 degrees of freedom, it will be 10 by 10 by 10, 1,000 grid points. So basically, if we assume this approximation and limitation, and we want to solve Schrödinger equation for hydrogen atom, we will need 1,000 points. It will be very rough and very ugly if one tries to do it. But it's much more grid points. But just as a general assumption, and number 10 is much easier for me to process in next example. So if we have molecular hydrogen molecule, we have twice as much electrons. Each of electrons 10 grid points. It is very, very rough. In practice, one needs more. So it will be 1,000,000 grid points. So we go from 1 atom to 2 atoms, and it's all jumping from 1,000 grid points to 1,000,000 grid points. So we can do it, but it is less comfort. And then we go to a single carbon atom. No one needs it. In our real world, in chemistry, atomic carbon is too active. It will immediately find a spot to stick to. It's maybe only at during nuclear explosion or something like this, exotic conditions. But it has 1s2, 2s2, 2p, total 6 electrons, right? No one objects. So everyone took some chemistry. You guys are ahead of me. I didn't took chemistry, except high school. So 6 electrons. Then how many grid points we need? Each degree of freedom, each electron is a vector of 3. So 3 degrees of freedom. So we need 6 times 3 will be 18. 10 to the 18 grid points just to solve Schrödinger equation for single carbon atom. How excited are we? And then practice the same thing for acetylene. And we are, well, I can do errors, but it comes to 10 to the 42 grid points. Maybe practical applications of acetylene do not justify this high level of numerical cost. We know it probably, if we would really need to do so, no one would do computational chemistry because it is maybe a little quicker to explore everything in practice in an experiment. So main challenge is the same as always, as we practiced during looking at nuclear degrees of freedom. Number of degrees of freedom. So for today's computational power, it is not practical to solve for such multidimensional functions. Although you are intelligent and educated enough to formulate such problem. If there would be enough computational power, you would be able to solve it. What do we do if number of degrees of freedom is too high? Right? So one may seek not like illness, seek like search. One may search for an opportunity to represent this function in form of products, or something like products, of elementary functions that depend on much less number of degrees of freedom. Right? Or functions that depend maybe only on position of one electron, or maybe even one coordinate. So what if one can, later on I will call this big phi. I didn't care at this time, but later we'll call this one big phi, and then here will be little phi. Little phi of R1, little phi of R2, little phi of R3, and they all are product. If this would be possible, we could separately solve Schrödinger equation for each electron independently, then multiply them and say, hey, here is our wave function. If it would be possible, then the course will be not 3 but 1 credit, and it would end within 1 month. You can imagine that it is not quite right. But general direction of thought is this way. So we need to find at which conditions we can use product form, or maybe adjust product form and find conditions when it is not as dangerous, or maybe find product form and formulate which correction needs to be added, or assess the amount of error in wave function in comparison between the pure complete wave function and the one that we built out of elementary building blocks. What did we do? We didn't derive any equations, therefore we did philosophy. Why? Why we cannot immediately represent wave functions as products of one electron orbitals of functions? Why cannot we select first electron system, second electron, fourth, whatever, and then assume that the electron number n has orbitals that do not depend on where other electrons are? Can we assume that if we ionize molecule and then put the electron back, the electron will not depend on what other electrons are doing? No. They repel each other, right? So electrons do interact. Therefore, they are not independent. And separation of variables in the form of product is available only if the variables are independent. If the terms in the operator, well, here we are not mathematicians, we are not in the differential equations, we are very narrow thinking quantum theorists or whatever, computational chemists. So not general operator, Hamiltonian. If the Hamiltonian operator would have terms that would consider terms, term 1 plus term 2 plus 3, that each term depends only on one independent variable. So if there is a sum of terms, each of which depend on one independent variable, then mathematically one can represent answer in form of a product of functions of independent variables. In physical chemistry, you did it for three-dimensional box, where wave function in each dimension doesn't depend on what is going on in other dimensions. So there is interaction, therefore the blind application of separation of variables is not allowed. Well, it's a free country, you are allowed to do anything you like, but it would not lead you to correct answer. It will not help to predict observables. Well, the goal is to attempt to represent overall wave function that we need to find, and later on we also need to find eigenenergy, but there is no reason to speak about energy before we have a clue about wave function. So we need, it is not our free will, it is we are mandated by the nature of our computers, who are so weak and cannot take wave function of 10 to 42 elements. So we have to represent wave function in something like product of some elementary orbitals. We need to do it. But we need a smart way to practice this product form, and the concept of Slater determinant will answer how to do it, how to construct the product-like form that will lead to minimal amount of errors. And we need to find a way to address influence of electrons to each other. If I invite you to look forward by like 2 weeks or whatever, the idea is that very simple. When we remove electron and put it back, at the instant when we put last electron to the system, it experiences repulsive forces from all other electrons that have been deposited, right? But we can remove not this specific electron, but another one. Remove and put back. And the idea is that one can formulate an average repulsive forces from all electrons inside. And then the orbitals for all electrons will have similarities. So one can split through this concept of averaging, one can formulate individual Schrödinger-like equations for building blocks for individual electron orbitals. This is not absolutely correct, and this is not the final answer. It is only the direction. So do not try to think critically and criticize. It's just direction of thinking. We'll go through details carefully and subsequently. Another area of our memory that we need to focus on. If you used to have a good teacher in your PChem class, which you may or may not, you need to memorize from the top of your head the equations for hydrogen orbitals. If you don't, it's not your fault, it's fault of your instructor. But when you complete your university degree in STEM, it is not a bad thing to remember. It's one of the few problems that can be solved exactly, and it is an important luggage of humankind knowledge. So since right now everything is very loose, we will come to rigorous logical steps later on. Now I'm hand waving and drawing general picture. So since humankind doesn't know too many exactly solvable problems for electrons, basically the only thing that we know exactly is hydrogen atom wave functions. We would like to use them as a basis function for each atom that is in our model. Or even if it is not exactly possible, to use them to make maximal use of our knowledge of these functions. So use hydrogen functions, find the protocol, how to construct overall wave function out of elementary building blocks, and take into account electronic interactions. So those are three aspects that narrow-minded quantum chemist needs to solve. Broad-minded quantum chemists also need to think about non-adiabatic couplings and nuclear wave functions. But this, if you learn how to solve these three challenges, if you will be able to browse through a couple of theories that address these three challenges, you can count on career and bread and butter. Okay? So basis functions, protocol how to compose big wave function out of small building blocks, and electron-electron interaction. So for several weeks and at least 2 months, we will be focusing on these aspects. When I was presenting this course for the first time, I was trying to avoid classroom teaching and go to conferences as often as possible, and I was leaving my first postdoc to present instead of me, and I wanted to give him credit. So Dr. Mikhailov was giving this lecture first time instead of me 7 years ago, and later on you will see a couple of nice images. So what if we will look on a single atom? Basically, in these three aspects that we need to cover, basis functions, hydrogen atom. Way to compose overall function as elementary outer elementary building blocks and outer interaction. Now we are going to quickly move on to the basic functions. So you know this reverted triangle which is gradient, right? If someone is lazy to write derivative d over dr, one can replace it with triangle. And there are even laziest people who replace reverted triangle with 2 by triangle L. Physics people know that.
Actually, I saw that in a math course.
Okay, so everyone practices. And then there are 2, so this is kinetic for electrons and this is potential. The electron-electron interaction and repulsion between electron and its nuclei. And here the church. So if we assume a crazy world where electrons do not interact with each other, where there is no, so this R sub ij means 1 over Ri minus Rj for relation. If we assume a world where electrons do not interact, where we have only kinetic energy and attraction of electrons to nucleus, we would be able to solve it almost immediately, or with like much more easier. We would practice products. We would solve individually for all orbitals. Then we would practice products and compose overall answer. So the absence of electron-electron interaction would make everything super simple. We know that it is light, that electrons do interact, voluntarily or involuntarily. But right now we are going to imagine it just for a minute, and in order to focus on the basis orbitals, our building blocks. So for what do you remember about atomic orbitals of hydrogen? Why should I speak about it again? I'm in presence of certified and educated people.
Just has one orbital.
Huh?
Just has one orbital.
Well, it is in ground state, right? But we know that if you excite hydrogen, there are several other eigenstates. If you do spectroscopy, if you like do UV excitation and then allow it to emit, there are like series, Lyman, Ashen, I don't know how to pronounce it. And this 1 over n square minus 1 over n square and some Rydberg constants in front for any spectroscopic transitions. So there are a set of orbitals for hydrogen atom. Their energies are formulated with some factor times 1 over n squared, where n is principal quantum number. And for each principal quantum number, there are some other quantum numbers that give us the spatial distribution along the angle. Right? As far as I know, this year in physical chemistry, there was no touch on the principal quantum number and dependence on distance from center of atom, but there was some discussion on the angular dependence. How 2 and 3-dimensional wave functions depend on angle. So all these things are combined together in the atomic orbitals of hydrogen atom. So which orbitals do you know? I better ask this. It's much more fun to ask those who know less. Therefore, for this chemical question, I probably need to ask someone from physics. You are the most physical representative of the group. Which atomic orbitals of the hydrogen are you aware of?
Are you talking about like spherical harmonics and?
Yes, but tell in simple language for everyone.
Well,
You
like
can
the-
hand wave.
okay, like the wave function can be broken up into two different components. One which depends on the distance from the nucleus, and one that depends on like the kind of like the angle. Yeah.
But if you would deliver this at kindergarten, how would you do it? Okay,
That's a good question.
Alisa, can you explain atomic orbitals of hydrogen? So that
Circle.
it's a first yes. So you can show, right? It is what it is. So first.
I don't know if that's what you wanted, but that's what I got.
Next one.
For what do you mean?
The P
Um,
orbital.
Oh, it's
See?
Oh yeah.
Okay.
Yeah, I see what you're looking
So
for
you
now.
can do this one.
Yeah.
Which one of them?
In the center.
There's 5 of them.
Yes, yes. So you intuitively know, or maybe much more than intuitive, what are atomic orbitals of hydrogen, right? And as Vijay did prompted us very correctly, for these three-dimensional shapes, there are two aspects. First, how the density of electron, probability of electron changes as we go away from the center. So if you go too far from the center, everything will be zero because of attraction to center. So it may be zero, not zero at center. It rises and drops, and then it's zero at infinity. And then as we go around the center, it may go to maximum or minimum. Right? Therefore, one gets these shapes. And if you carefully, rigorously solve for hydrogen orbitals, you'll find that these shapes can be literally exactly specified by how many quantum numbers?
3.
Yes, if you forget spin, then 3. What are those quantum numbers?
Energy,
Principal,
the
angular, and magnetic.
Yeah.
Right? So principal is energy, angular is amount of angular momentum, and magnetic is projection of on the LZ, on the Z axis. Right?
sure.
Yeah.
I will, for next years, I need to make sure that this is everyone who exits PCAM1 knows it. We were discussing what is written here. N for principal, L for orbital, M for magnetic. Right? And here is the dependence on position, which depends on principal and orbital. And here the spherical that depends on angular and magnetic. Right? So you shouldn't be surprised when you see it again. And you shouldn't be surprised when you see these images. So it is what Alisa was showing. What is green and what is red? And I know that one of you is doing serious investigation of this question. So it's not as simple as we can look on the first glance. Well, if we look not on the density of orbital wave function, but on the wave function itself, and by some reason we forget about complex part, then it can be either positive or negative. Because after taking square, all negative will become positive. So positive and negative, or maybe negative and positive. So green, the color codes stands for sign of wave function. Here you can torture instructor at this point and ask if you were very carefully looking here, you may find an inconsistency. So if one is looking, no, the inconsistency is here, but the details is not sufficient to catch. If one would look on the explicit form of the spherical harmonics, or if you remember the wave function for three-dimensional rotations, two-dimensional rotations, you remember that it is complex. It is like e to the power magnetic quantum number and then n. And when we go here, you see only real and not real energy, the positive and negative. There is no imaginary part. There is one trick that is very often skipped in textbooks. The exact literal solutions of Schrödinger equation that has this imaginary part are then processed with one additional step. They are combined in linear combinations. So the values for magnetic quantum number of the same value but opposite sign, plus and minus, are combined together as summation and subtraction in order to form, and as a result, due to Euler equation, one is getting the wave functions that are real. And then they do have these nice shapes. If you would plot, it's not possible to plot wave functions that come literally from solution of Schrödinger equation. They are imaginary and you cannot plot them, they would not look nice. But after this additional protocol of adding or subtracting orbitals with same value but opposite sign of magnetic quantum number, one is getting these shapes. And true chemists also have a nomenclature for each of these orbitals, like px, py, pz, right?
Mm-hmm.
And do you know nomenclature for d orbitals?
It gets funky.
I will not catch you, just give general.
X, Y, Y, Z. Yeah.
So it deals which plane it is at or which plane it intersects. What is the abbreviation for this one as a donut?
Z squared?
Yes. And most people hope that for the rest of their life they will never see at orbitals. Okay. So why do we need them? We hope, and we do not have much freedom, that we can assume that at each atomic center, at each nuclei in the molecule, we do have a set of such orbitals. And whatever electrons are available for the system, we will place them at such orbitals. And then multiply these orbitals by each other and obtain overall big wave function of the overall molecule. I'm lying. I'm not telling you exactly. It is just general direction. Well, not lying. It is too strong approximation. There will be important things that we add to this idea, but general idea is correct. So we are going to assume that at each center, like if you have a satellite, 4 centers, 4 ions, at each ion we do have set of these orbitals and we just populate them with these electrons. And then each of the populated orbitals is multiplied to each other, and then you have multidimensional wave function. If you literally will do it, the results will be very far from reality. But with not very complicated corrections, this can be done. So just please set up your minds to this direction. Now we are unsupported. Tech support. What is next? Many electrons, products, Slater and Powell principle. Well, here are a couple of images for radial shape of wave functions. For s orbitals, it is non-zero in center, and then it drops. And for p, no, I think it is for s orbitals with higher energy. Non-zero, zero, and then again something. So if you look on these orbitals, if you can go through them, it means like something, then nothing, then again something. It's like egg in a shell, right? Or, and here is 4p orbital. So nothing in the center, but then something, and then nothing. And when you go around, it also modulates density. So that one gets this, how do you characterize this shape? By word now.
For like, for d orbitals or?
No, for p orbitals, which natural object from regular array?
I mean, I would say it's like kind of infinity type thing.
Okay, infinity type orbital. Good. Infinity orbital. If you are going to gym for weightlifting, right now, these tools for one hand are more cylindrical, but historically they were just cast iron from two spheres and connection, so they were looking very like p orbitals. Okay, atomic orbitals are centered around each other. I have heard that in CHEM476 you have already discussed the anti-symmetry.
Yeah.
Good. Can you share?
I sort of remember, I mean, anti-symmetry goes along with fermions, and it's discussing how the order matters in the way you put things into the states.
Mm-hmm.
Because you have to worry about the up and down arrows, while with the symmetry, you have bosons, which order doesn't matter because you can have up, up, or up, down, or any of those.
Okay, yeah, thank you. I'm happy to hear the keywords that I recognize. No bosons for today, and for this course, only fermions. So, anti-symmetry of what? Or of who?
Electrons.
Yes, anti-symmetry of electronic wave function, of multi-electron wave function. So, can we establish a shop of electrons and sell red electrons 5 cents per piece and blue electrons 10 cents per piece? Can you distinguish between electrons? So they're kind of similar or equal. Are we allowed, if you have a H2 molecule and you have green electron on the right and blue electron on the left, can we swap them? Huh? You can imagine that we are swapping them. And properties of molecule shouldn't change if you swap. So there are several electrons in molecule. What changes if we swap two of them? For example, let's think that we have a wave function that depends on two electrons, first and second. First at position 1, second at position 2. What will be the density? Electron density which influences the most of the properties of the physical properties. So density will be equals absolute value squared of 5 or 1. So on the right side, I practice the same function where arguments are in different order, which means I took electron number 1 from position 2 and placed it in position number 2. swap them. Okay? So this is argument first, this is argument second. I swap electrons. Will there be any change in the density? So if you formulate the probability, absolute value square. This is line. This is straight line. Just in case. So, if we want to believe that electrons are indistinguishable, then wherever the order is, the density should be the same. Right? And our requirement of this indistinguishability of electrons, we have right only to require it for observables with density, but we do not have right to require too much from the wave function. So it would be, this is the hardest part in whole quantum theory. I do not understand it. I'm telling it to you as a parent. So we can require indistinguishability only for observables. We cannot require it for wave function. But this requirement can be satisfied in cases if after swapping they're the same or if it changes sign. What else? I'm going to introduce the functional form that helps to construct multi-electron wave functions of the single electron orbitals and give some non-rigorous idea why this shape is correct. This is a big finding. There were a lot of efforts to find this shape, and if we just check that this shape is not violating any of our beliefs, we can use it further. But don't request literal proof. So this shape that you will see soon, just keeping it in. This shape should satisfy these ideas of undistinguishability of electrons, and it should satisfy principle of whom? Yes, Pauli principle. And Pauli. Which tells what?
Can't have two electrons sitting in the exact same state.
Yes, everyone agrees. Just wondering. At least on this subject. Okay, no electrons in the same state. No electrons with the same set of quantum numbers. Good. And also, 1, 2, 2. And wave functions should be normalized. So if we have wave function with index 1 for electron number 1, and we have wave function 2 for electron number 2. But if we swap their order, the sign should be minus. Wave function 2 for electron number 1, and wave function orbital 1 for electron number 2. This is worth of writing down if you see it for the first time. If you see it for the second time, I don't know what you're doing here. I offered you to So write it down. I will try to minimize any homeworks, exams, and quizzes, but you may face necessity to practice this equation in other courses or somewhere else in your life. And since if there are only 2 electrons, there should be a normalization factor. So I'm going to mumble something for another at least 10 minutes, but you will not hear anything new. We will just discuss this shape and look on its property and whether it satisfies this undistinguishability, power principle, and normalization. Well, this is from normalization, so it's fine. And we need to cover the first 2 things. I probably can do Pauli right now without even putting it. So with indices 1 and with positions 1 and 2, we are indexing, we are indexing different electrons. And for this orbitals number 1 and 2, or we can put A and B, I and J, some indices, we are resembling ions where it is located and set of quantum numbers. So if suppose that we want to violate Pauli principle, how can I violate Pauli principle?
Phi1 bar 1 is equal to phi2 bar 2.
Yes, I can violate Pauli principle if I assume that both first and second electron are both on the first orbit. So this graph is to violate Pauli. Principle. I need to edit the recording. So you have same function 1 and 1, and you have function established at different positions, but phi1 r1, phi1 r2 product, and you can swap the order of functions. Phi1 r1, phi1 r2. These two are equal, so when you subtract, it will be 0, right? So wave function equals 0. No, it's annihilation. It's like vacuum. It means no wave function. So there is some nonsense. Wave function, when it is defined, it should be something non-zero that you can integrate and get 1 to the noise. So if you try to go against Pauli principle, we are getting mathematical nonsense. We are getting that wave function equals 0. 0 everywhere. So since we came to nonsense, it means that we did the wrong thing. Therefore, if we accept this functional form and we require that orbitals will be different, first and second, I and J, this functional form will, for multi-electron wave function will not violate, will obey Pauli principle. So done with normalization, done with Pauli principle, and for undistinguishability, I think if you recall this one 2 and this one 1, this one 2 and this one 1, we still will have subtraction of two terms. Same functional form. So it also follows indistinguishability. This was again not derivation. We just discussed functional form and did some philosophy that it doesn't breaks any of our. It goes along with whatever we believed before. I was asking myself, is there a way to literally derive this functional form in some similar problems? And if you want to stay on the academic career and you are thinking about taking upper level courses in the future, I can navigate you to a place of knowledge where you can get literally this answer without any philosophical input. So when you consider two systems of two non-interacting spins, up and down, two states, and find all possible eigenstates for this system for non-interacting spins, one is getting answer that it can be singlet or three states for triplet. And one is looking for literal wave function of two spins for singlet by diagonalizing the full spin squared matrix. One is getting exactly the same answer. So without any philosophy. What's the connection between this functional form? I just replaced here phi 1 and phi 2 to G and F. But what is the connection to the word determinant?
You can construct a 2x2 matrix with f of R1 as the top left element, G of R2 as the bottom right element, and then I think it was f of R2 in the top right and G of R1 in the bottom left. And then if you take the determinant of that, you get the entire, you get the difference inside the curly braces. And then if you put a 1 over square root of 2 factorial outside the determinant, you get the 1 over the square root of 2.
Mm-hmm. Did you get it? More or less? So this magic functional form, or this nice, helpful functional form, in this class, we didn't touch where it comes from literally. We just provided philosophical background. In some upper level courses, it can be derived by addition of spin angular momentum for two spins like half. And again, just for memorization or for quicker construction of this functional form, one can observe that it is identical to the definition of determinant for 2x2 matrix. Okay? We'll do together.
No,
Let's you help.
Why me? I get it done so much.
If you do it, then you'll teach the whole class.
Well, they already.
No one volunteered.
I haven't.
You're the most bravest in the class. So
You are a freshman in this class.
Did you saw it before?
No.
Oh, okay. So when you see these writings, the matrix and determinant, you take things which are like a diagonal and
Oh, yeah,
multiply
okay.
8 times.
Find the totals.
You mean quantum 2?
Yeah.
We had a 3x3.
I
Yeah.
remember doing one
Excellent.
bigger
Thank
thing.
you so much.
Only a
If you are sitting not in the middle of the row, but on the edge, you are in the risk group.
Paper animals.
No, I'm good right
So,
want me to write a matrix at the bottom?
Yeah.
yeah, just write what goes here. So, if it is a determinant of 2 by 2 matrix, Alyssa taught us that you take elements that are on diagonal product minus elements that are off diagonal product.
Those are B's, right?
Yes.
Okay. I don't know if they were.
So the matrix is a multidimensional object, and we need to convert it into, how to say, radical, just scalar function. Minus. Okay, that's it. Yeah, thank you, Daniel. And I'm allowed to just freeball as we add 1 over square root. So, yes.
I just have a quick question. I've been confused where are you getting like the 1 over square root 2? And I know it's like the normalization constant,
Yes.
but I don't understand why you have that value.
Good idea for next homework. If you take this wave, so if you take this wave function R1, R2, absolute value squared, dr1, dr2 to integrals, it is mandatory must be equal to 1 as each wave function. And if you practice and you know if that each of the individual atomic orbitals is normalized to 1, you may get this, you may satisfy this requirement only if you multiply the overall stuff by 1 over square root 2. So let's look back on what Alyssa and Daniel instructed us. So if we formulate a matrix of the orbital, first orbital and second orbital, evaluated at different positions for different elements. First element position 1, second element position 2. Just, it's abstract exercise. And just formally practice the definition of determinant. So this is 4 cells into this 2 by 2 matrix, and we practice definition of determinant. This 2 product minus this 2 product. Suddenly, oh, we already saw it in the previous slide. It is a Slater determinant, right? So it is a way how to construct multi-electron wave function out of atomic orbitals that will satisfy normalization, undistinguishability of electrons, and Pauli principle. Why? Why do we care about torturing young brains with this complicated form? Why did we suffer necessity to come to the blackboard and write? Why are we not satisfied with the writing on the previous slide? Why do we need determinant and matrices?
It generalizes it to more than 2 particles.
Yes. Are you agree with London? At least in this aspect? So, we philosophically set up the functional form only for 2 electrons, but sometimes we have much more than 2. And we are not proving it here, but it is the heritage of previous generations. If you practice this rule for more than 2 orbitals and more than 2 electrons, the wave function constructed as a determinant will satisfy normalization, undistinguishability, and Pauli principle. So it is a general principle for any number of electrons and any number of orbitals. 2, 3, 4, 5, 100,000. And it consists of several products in different orbitals. Not just one product, but several. The larger the number of electrons, the more products is are in the Slater Orbitals. Exchange of particle doesn't change result of measurements. Yes. You already checked. Yes. I think we can finish now. We all sides of a trench entirely. So many thanks for coming. I'm going to collect homeworks. It's so nice that I haven't forgotten to do it. And I look forward to see all of you on the lab on Wednesday night.
The first figuring out
You can email.
Okay.
Okay, meeting is done. I'll stay here to answer questions.
You're already great.
Yeah, because I just mean, like, I don't wanna do it, like.
I'm not gonna meeting with them.
It's good. Did he say that?
I mean, if
So,
you
good idea.
It's like for the beginning, but usually at this point.
and then we can find out if the person got it. I know that was like an hour earlier than how to go.
Data is
Yeah, it's right.
Yeah, I mean,
Yeah.
I don't know. 'Cause, like he told me that they already